Okay, welcome to the second part of Unit 10. In this second part, we are going to be looking at examples involving work. So here is our first example. What is the minimum amount of work I must do to lift 10 kilograms from the floor to above my head? That's approximately 2 meters up. So what does this look like? This looks like here I have a 10 kilogram mass. And here's me bent over trying to pick it up. And it ends up with me being triumphant, holding that mass above my head. And I think my arms look like they're Gumby here. And the distance between where the weight here started and where it ended is about 2 meters in distance. If we think about the free body diagram of the object, it has two forces on it, ignoring air resistance and things like that. It has the, I'm going to go with M for mass, 10 kilogram mass. It has gravity acting downward, and it has a normal from me, which I'll just use P for person here, on the mass. What this question is wanting to know about is how much work must I do, which involves this normal force. But I don't have a good way of knowing that normal force here, which is why it also is putting in the words minimum amount of work. In order for it to be the minimum amount of work, that is the situation where there's no net force, which means since the weight force is mg, or in other words, 10 kilograms times 9.8 meters per second squared, or 998 newtons. Then this also must be 98 newtons because F net equals 0 newtons when it's looking at the minimum amount of work. I can now plug this into work is FD cosine of theta. Oh, I got to worry about this angle. Well, my force is acting upward, and the block's velocity has to be upward to go from the ground to above my head. So the angle in this case is 0. So we have a force of 98 newtons times a distance of 2 meters times a cosine of 0 degrees, and that's 196 joules. Okay, that one was fairly straightforward. In the next one, we're going to deal with something a little bit more complicated. Here we're going to have a boy in a wagon. So here's my wagon, here's my kid, arms on his knees, here's the handle of the wagon, here's me pulling the wagon. And I tell you specifically that this angle is a 60-degree angle. Okay, so we're going to pull on the handle of the wagon, and I'm pulling with 100 newtons for 20 meters, but I also want to know how much work friction does. Okay, well, again, starting with the free body diagram, we have a normal from the surface on the wagon. We have the wagon's weight. We have friction opposing the wagon's motion. And then we have a normal from me, we'll go with person on wagon again, that makes a 60-degree angle, and this is the one that you are told is 100 newtons. Okay, so the last thing before I flip slides that I want to point out is these words constant speed. So remember, constant speed means F net is 0 again. There are two ways to approach this problem, and both are valid. So the first way is to just use the definition of work. Okay, so work is FD cosine theta. In this case, the angle, the force is the normal from the person on the wagon. We've got the distance, and now we need the angle. Well, what I know is that the velocity is horizontal, and the normal from the person on the wagon makes a 60-degree angle between, or with the horizontal, which means we can plug in 60 degrees as being what theta is. What angle does the force make relative to the velocity? So this is 100 newtons times a distance of 20 meters times the cosine of 60 degrees. And when you put that all in, that is 1,000 joules. Okay, that's method 1 for part A. We will get to part B where we look at the work by the force of friction here in a minute. But let's first move on to method 2 for doing part A. So for method 2, part A, what I know is I know that I have a normal force equaling 100 newtons. But only the x component is going to do work because that is the piece that is parallel to the velocity. So that's going to be NPW times the cosine of 60 degrees. So 100 times the cosine of 60 is 50 newtons. And now I can say work is FD cosine of theta, where my force is just the x component. And my angle in this case is going to be 0 degrees because my x component is parallel or in the same direction as the velocity. So now we take 50 newtons times 20 meters times cosine of 0 is 1, and that is again 1,000 joules. Okay, we've got part A done in 2 ways. Let's now move on to part B. How much work does friction do? So for method 1, part B, what I need to realize is because F net equals 0, that means that the work done by the net force, cosine of the angle between the net force and the velocity, is going to be this angle in this case. But because the net force is 0, the work has to equal 0 as well. Okay, but I know that the work done by the person is doing, or the person is doing work, but friction is also doing work. So the work by the person has to equal the work from, or plus the work from friction has to equal 0 joules. And so we get the work from the person, backwards. The work due to friction is the negative of the work done by the person, which is going to be negative 1,000 joules. Where this negative sign means, as we'll see a little bit, that it's taking energy out of the system. Method 2. Method 2, I say, okay, well, F net equals 0 newtons. I know the normal from the person on the wagon, therefore has to equal x component, has to equal friction from the surface on the wagon. We just found that on the last slide to equal 50 newtons. Those friction from the person on the wagon equals 50 newtons. I can now say work is going to be FD cosine of theta. My force here is the friction, my distance. My angle is going to be 180 degrees because it is again a case where the friction points this way, but the velocity points that way, therefore 180 degrees. So 50 newtons times 20 meters times cosine of -1, or cosine of 180 is -1. Therefore, this is -1000 joules.